many of us at least spent some time in the Midwest, and this was true of Professor Neiberger, who received both his bachelor's and doctoral degrees at the University of Chicago. He's been at UCLA since 1941, is now professor of meteorology, chairman of the Department of Meteorology 1956 to 62. Unlike some of us, he's been burned by the fires of much practical experience. He worked for the U.S. Weather Bureau for 10 years. He was on leave for 2 years with the Air Pollution Foundation, 1954 to 1956, and he's been a consultant for many public agencies, including the Los Angeles Air Pollution Control District. His eminence in meteorology is attested to by membership in many societies, and he has been president of the American Meteorological Society and the section of meteorology of the American Geophysical Union. I think if there was one phrase to properly describe Morris Neiberger, it would be that he's certainly a devoted public servant. He is one of the more active people in the academic senate at UCLA. Although his main interest in meteorology is not smog, he's been a prolific researcher in many phases of meteorology, but he has adopted smog. He's adopted this problem and spent much time and energy on it. The impetus for the development and organization of this lecture series on pollution and conservation generally, in fact, came from him. So without further ado, I'll introduce Professor Morris Neiberger to speak on prospects for clean air.
Professor Hockey. The smog problem doesn't appear to be quite as much of a burning issue now from the standpoint of the attendance here. However, as we'll see, a good part of the smog problem is the result of burning, combustion of one sort or another. Before I start, well, I was sort of hoping that we would have a period of typical Los Angeles weather so that I could ask you how long it was since you took a deep breath, because during much of the year we go around, we don't actually hold our noses, but we breathe very shallowly because it becomes very unpleasant to take a deep breath. But just to illustrate what I'll show a little later, that meteorological conditions are an important aspect we've had for the past, actually for the past few weeks, rather favorable weather from the standpoint of not having high concentrations of air pollution, and this is characteristic of some of the period winter and early spring here in Los Angeles. But starting, say, in mid-June and lasting through at least part of September and then occasionally into October and November, I can predict with with almost absolute certainty that you will be experiencing this condition in which you will be going around and trying to avoid breathing. Well, what is the reason for this situation? The reason is twofold, as I say. One of them is the meteorological conditions, and we'll consider that second. We'll go into a little detail about the reason why the atmosphere doesn't have an unlimited capacity for pollution. You can't just pour contaminants into the atmosphere at liberty and expect to have this swept away and constantly diffused and dispersed and removed, and you then constantly have tolerable conditions. The reason for this, as I say, is the meteorological conditions. But the other contributing factor to smog is the fact that in human activities, particularly in modern civilization, when we depend so much upon sources of energy, and these sources of energy are concerned with fossil fuel, the burning of fossil fuel, the source of our energy is also the source of a great deal of the pollution that we're concerned with. And just to illustrate that, well, let me mention, in case I'd assume that looking at the age of the audience, I wouldn't have the problem that I had in my class the other day when I said something about the burning of fossil fuel, and a hand went up, and the question was, what is fossil fuel? And then when we were up at the colloquium over the weekend, and the kids were making snowmen, and one of the little boys was asked by my wife whether he was going to build a snowman. Oh, he couldn't build a snowman because you had to have a carrot for a nose to build a snowman. And so I said, well, I would have thought that he would have said perhaps you had to have pieces of coal for the eyes, but then the chances are the child doesn't know what coal is. Well, fossil fuel consists of these minerals which we burn, namely coal, petroleum, and natural gas. And the first of the slides, the first slide please, just illustrates how the consumption of these has been increasing during the past, well, since the beginning of the century, actually since 1899. This is a slide I prepared a number of years ago, so it only goes to 1949, a half century. And you see that coal during the first part, right up to during World War I, there was a rapid increase in the consumption of coal. Millions of tons. The amount is expressed in this fashion. I believe in the other room they have one in terms of amount of energy coming from coal. At any rate, the consumption of coal increased very rapidly, leveled off during the 20s, went down greatly during the Great Depression of the early 30s, and then gradually rose and has been roughly at this level ever since. But at the same time as the consumption of coal has leveled off, the use of petroleum has been increasing, and you see the continual increase until it gradually begins overtaking. And then the next slide, which covers roughly the next 10 years, but begins in 1930. And here on both rooms it's in terms of amount of energy, because I wanted to show the use of natural gas too, and we don't speak of natural gas in comparable quantities of tons. But you see that coal has remained roughly level, falling off just a little in the 50s, but not much change in amount of energy from coal. Oil, or petroleum oil, has been increasing continually, and natural gas, starting at a much lower level, has also been increasing until between the natural gas and the petroleum, the fuel oil, you have more than twice as much energy as comes from coal, and this process has continued. And it turns out that in the burning of all of these substances, as we'll see very soon, there are products which are of some have undesirable qualities when they get into the atmosphere. Natural gas somewhat less than these other substances. Well, this has to do with the broad sources of energy. But there's one particular source of energy which is of extreme importance so far as the Los Angeles community is concerned, and that is the source of energy for locomotion, for driving our automobiles. The next slide shows us something about well, actually it shows us not only what has been going on, but also what is projected. And here you see well, first of all, we might look at the population trend. The population here in Los Angeles County has gone up from 2.5 million at around 1940 to about 7 million at the present time. The number of automobiles, which was stationary during World War II at a little over 1 million, has climbed to almost 4 million by the present time. But you'll notice that the consumption of gasoline, which is this line that starts at about 2 million gallons per day, has climbed even faster than either the population or the number of motor cars. And the consumption of gasoline now is close to 8 million gallons per day. And this gasoline is burned only partially by the vehicles which we drive. Roughly 10% of this, roughly 800,000 gallons, then 1/10 of this almost 8 million gallons per day goes into the atmosphere unburned. Now, I told you that we'd look at some of the contaminants that come from coal, oil, and natural gas burning, and we see that on the next slide. I had another slide which outlined in great detail all the minerals that come from this, including practically every mineral that you can name is included in the fly ash that comes from burning coal or oil. In the case of coal, burning coal, we haven't burned coal in this county to any extent for perhaps 60 years, but we used to in the early days. Now we don't burn coal, but in places where they burn coal, they get a tremendous amount of carbon floating in the air, what is commonly called soot. And this actually is expressed in terms of pounds per 10 million BTU of energy, again to make the coal, oil, and gas comparable. And you see that in the case of coal, you get about 11 pounds per 10 million BTU, whereas in the case of oil, you get only about 1 pound. So oil is much better than coal so far as the production of soot is concerned. The same thing is true in the case of fly ash. Only about 1/10 as much fly ash from coal as from oil. Now, these quantities here, sulfuric anhydride and sulfur dioxide, we'll see down here. But these quantities, this little dash doesn't mean that there is none. It just means that in the study that was made, they didn't make measurements for these. So I would guess that the same thing would be true as in the case of these other quantities, that you get about 10 times as much from, or perhaps only 5, but a considerably larger amount from coal than from oil. So we benefit greatly from the fact that even when natural gas is not being used, we are getting much less than if they had been using coal. Well, now in the case of natural gas, all the particulate matter, all the solids that occur and form smoke that you can see, these are much less altogether than oil, perhaps considerably less than 1/10 of the amount that comes from oil, and considerably less than 100th of what comes from coal. So from the standpoint of particulates, the burning of natural gas is greatly to our advantage. Gaseous contaminants, now again, in the case of the coal, these dashes do not mean that there is zero of these quantities. It just means that they weren't measured. But you see that in the case of sulfur dioxide, the average coal has somewhat more sulfur that burns and forms sulfur dioxide, which is an unpleasant and actually a poisonous substance in high enough concentrations. Oil has somewhat less sulfur dioxide. Natural gas has almost none. The same thing is true of the sulfur trioxide, since it comes about by the oxidation of sulfur dioxide during the burning. Oxides of nitrogen are formed not by a component of the fuel, but actually by the process of burning at high temperatures. The nitrogen, in a certain amount of the nitrogen in the air is combined with the oxygen in the air when you have any combustion at high temperatures, and that forms oxides of nitrogen, usually nitric oxide, NO, and then that in the air goes over into NO2. But the amount in coal burning, if it's at about the same temperature, would be about the same as in the other cases. And I don't know how realistic these differences are, but you see that there's a little benefit indicated from using natural gas even for this, but probably not necessarily, these may not be truly comparable figures. At any rate, you see some of these substances that come from burning coal or oil, and you get some of these also from burning natural gas, but not as much. Now, when it comes to driving the auto, we have a similar problem. The next slide. This shows it's actually a little more detailed than I would have liked, but I didn't have a slide which was simple enough. I just want you to focus your attention on the exhaust analysis, which is about halfway down, which says carbon monoxide, CO, carbon monoxide. And this is in percent. 4 to 6% of the exhaust is composed of carbon monoxide when your car is idling. And under accelerating conditions, somewhere between 0 and 6%, and similar percentages in cruising or in deceleration, so that something of the order of 4 or 5% of the exhaust gas usually is carbon monoxide. Oxides of nitrogen, which are formed in the same way because your car burns the gasoline at high temperature, has relatively smaller quantities. You see, it's parts per million. This is parts per 100%, and this is parts per million. So these are quite a bit smaller quantities, but you see they are not inconsiderable quantities, particularly when your car is cruising, which we hope you do most of the time. Of course, if you're making stop-and-go driving, then you're doing stop-and-go driving, then you're going between idling, accelerating, and decelerating. And but you see that something of the order of perhaps 1,000 parts per million, or 1 part per 1,000 of the exhaust is composed of nitric oxide. And then the unburned gasoline, the hydrocarbons, in parts per million. You see, when you're idling, you lose quite a bit. And when you're accelerating, somewhat less. When you're cruising, sort of also somewhat less. But when you're decelerating, when you're coming to a stop, then quite a bit more. And the expression of this in terms of unburned fuel, the percent of supplied fuel is shown in the bottom line. When you're decelerating, perhaps more than half of your gasoline comes out the tailpipe. When you're going through the other parts of driving, maybe 2 to 6%, say an average. For all the phases, the average is estimated to be about 7% if your car is in good condition. If your car is missing, well, if it's a 6-cylinder car and you're missing, you're losing 16% just by one cylinder missing, and so on. So that the average of cars on the road is probably considerably more than 7% of the exhaust, 7% of the fuel going out unburned as exhaust. Now, in addition, there are crankcase losses and evaporative losses. The crankcase losses on all cars later than I think about 1962 are taken care of by a crankcase device here in California. And in fact, subsequently, something like 1965, the motor industry has put this crankcase recirculating device on all cars sold in the United States, so that the crankcase losses are no longer to be considered a major source. But at the time when both crankcase and evaporative losses were added to the unburned fuel, the estimate was that 10% of the gasoline which went into your tank went out into the air. I think most of you are familiar with the fact that these hydrocarbons which go into the air and the oxides of nitrogen engage in a photochemical process which produces all kinds of changes into very noxious and obnoxious substances in the atmosphere, causing the eye irritation, the irritation to the nose and throat membranes, the whole respiratory tract, causing nausea and headache, many symptoms when they're irradiated by the sun. And so this is the special character of the Los Angeles type smog, which has now been experienced in most places of the earth. Well, so much for the makings of smog, the stuff that goes into the atmosphere. Now I'd like to turn attention to the thing that I'm somewhat a specialist on, namely the meteorological aspects, the reason why the atmosphere can't take an indefinite amount of pollution. And this has two aspects. One is sort of a local aspect, you might say, and the other is a worldwide aspect. And we'll talk about the local aspect first, and that for that there are two phases. One has to do with the up and down motions of the air, and the other has to do with the horizontal motions of the air. You see, if you can put material in at the ground and it gets mixed up through the entire atmosphere up to 10 miles or 15 miles or more, then relatively little stays down near the ground and the conditions aren't so bad. On the other hand, if there's a strong wind blowing so that the pollution goes in but is spread through a large amount of air which sweeps past these sources of pollution, then too there's a great dilution takes place, and the amount is very little. The amount the concentration is very little. The characterization that's usually made is supposing that you have a room with a bunch of cigar smokers, let's say. It'll be very unpleasant if the room is low and you have the windows closed. If you have a high ceiling, a lot of the smoke will spread up to the upper part and it won't be quite so bad. And then if it gets bad and you open the windows so there's a ventilation carrying it out of the windows and new fresh air coming in, then even though the smoking continues at the same rate, there's much less pollution, less concentration of pollution, and the accompanying eye irritation and irritation to the membranes is much less. Well, just to show how the atmosphere behaves in respect to a low ceiling, the next slide illustrates various types of temperature variation with height. There are three different graphs here. The graph on the left is what we call an unstable condition. The graph in the middle is a normal variation of temperature with height, and the graph on the right is the inverted condition, the condition of an inversion, as we call it. Now normally, this middle, as is shown in this middle graph, and this happens to be in degrees Celsius and in height in meters. Well, 100 meters is a little over 300 feet. I think you're all aware of that, so you can do the conversion for yourself. And 15 degrees, for instance, would be 59 Fahrenheit, and each one of these then can be considered almost 2 degrees, 1.8 degrees Fahrenheit, if you prefer to think in terms of Fahrenheit. At any rate, in the normal condition shown in the middle of this slide, the temperature decreases with height, but not extremely rapidly. And so in such a case, the temperature might be 17 degrees at the ground and drop off to maybe 12 degrees by the time you reach 10,000 feet and 3 kilometers. Well, I beg your pardon. This is 12 degrees by the time you reach 800 feet. This is a typical variation. Now, it turns out that if you take a piece of this air and lift it, it will cool at the rate of 1 degree per 100 meters. So this little dashed line is to suggest that we have taken somehow or other and given a little piece of air at this position where that dot on the line is, the dashed line leaving it represents the change in temperature of a parcel of air as it is given a little push upward and goes to 100 meters higher, from 300 meters to 400 meters. It will cool 1 degree, and it starts here at 15 degrees and it reaches that position at 14 with a temperature of 14 degrees. But the surroundings, where the temperature only decreases 7/10 of a degree in the same distance, that will be warmer. And so when this parcel of air reaches this position, it will be colder than the surroundings. If it's colder, it'll be heavier and it'll tend to fall back. So that this is what we call a stable condition, a stable air column, where if you displace a parcel, it gets it gives rise to a force that tends to bring the parcel right back where it was before. And under normal conditions, it takes a pretty good push to cause air to move up and down, but if there are pushes, as there are when the air moves over buildings and so forth, the air can mix with the surroundings before it bobs down, and so there's a certain amount of mixing going on under normal conditions. If we go over to this left side, you see this is a case where the temperature decreases much more rapidly with height. It goes all the way from 18 to 12 degrees in only 500 meters. And so if you now take the same situation of a parcel of air at 300 meters, displaced 100 meters, it arrives at the position, well, I guess it starts at 14.5 degrees, it gets to 13.5 degrees, but the surroundings are colder than that, and so this displaced parcel now is warmer than the surroundings, and it'll tend to continue going. And that's what we call an unstable condition. And then finally you come to this inverted condition, the inversion, where the temperature actually increases with height. And then if you displace a parcel of air along this dashed line, the temperature change would be shown as on this dashed line, and it would be, if it's displaced in this particular case 100 meters, it would be 2 degrees colder than the environment, much heavier, and it would fall right back. So it would take a tremendous amount of a push to cause it to be displaced in that way, and it wouldn't be displaced very much. The result is that an inversion tends to act as a damper on any up and down motions, and in fact, where there's an inversion, if you put in pollution at this position, it'll stay right at that level. It won't tend to go up. If it tended to go down, incidentally, it would find itself warmer than the surroundings and tend to bob right back. So this is a very stable situation, and the pollution stays where it's put. Well, the next slide shows a typical variation of temperature with height in the Los Angeles area. This happens to be a sounding for Santa Monica, July 1st, 1957. It happened to be one that I had readily at hand on top of a pile of ones for July, so that's the one I took. And this is typical throughout the summer months in coastal regions of Southern California. You have in this lowest layer a normal or even an unstable condition up to a height of about 400 meters. You see here we have the height in kilometers on the left scale, and then inside the height in thousands of feet. So something above 1,000 feet, say about 1,200 or 1,300 feet, is the position where this change from a relatively unstable layer to an inversion occurs. This layer here is called an inversion. Actually, the temperature continues rising up to about this position, and then you get a sort of a normal lapse rate, a normal decrease in temperature from there on. Now, this lowest layer will permit mixing to go on, and pollution which comes in at the ground can mix up and down to this level here. And illustrative of that is the numbers on the right of the curve. These numbers represent the relative humidity. And the water vapor, which is introduced near the ocean surface, at the ocean surface, then mixes up quite readily also, so that you have humidities in the 80s right up to the base of the inversion. But from there on, the mixing is damped, and you have humidities above, way down at 18% and 12% and so forth. So this is the typical condition where you can have mixing going on in the lowest 1,000, 1,500 feet, and above that a lid, an inversion, which keeps the mixing from going any higher. The next slide is I've put in to emphasize the fact that this isn't something that occurs just at Santa Monica or just in downtown Los Angeles. This is the way the atmosphere is all the way, in this case, from San Francisco to Honolulu. Height in meters versus distance. And these lines are isotherms, lines of constant temperature, so that, for instance, if you were to be right at this position where it says 35.9 north and 130 degrees west, and you go upward, you see you start at 17 degrees, and then 16 and 14 and 12 and 10, and finally a little over 8 degrees, and then you go right back up at 10, 12, a little more than 12, and then you get. So this shaded area is the layer with the inversion, the layer in which the temperature increases with height instead of decreasing. And this layer then extends, as you see, all the way. It's about 400 meters at San Francisco, and it extends, slopes upward, but extends all the way out to Honolulu. But at Honolulu, it's all the way up at 2 kilometers, almost 7,000 feet. And so you have a pretty deep layer for the pollution in Honolulu to mix through. But here on the coast, it's much lower, only about 13 to 1,500 feet in which the mixing can go on in a average summer situation. Well, it isn't so bad if the inversion, well, it isn't terrible, let's say. It's bad enough if the inversion is at its normal height of about, say, 1,500 feet in summer. But some of the time it's higher, and then we're a little better off. It's present throughout the summer months with almost no breaks, but sometimes it's higher, but quite frequently it's much lower. It'll be down to 500 feet above sea level, or even lower than that. And when it's that low, then you get the severe smog attacks, because then you have the inversion so low that there's a very shallow layer through which the pollution can mix. Well, I mentioned something about the fact that if you have good ventilations, if the window is open and you have a fan blowing fresh air into the room, then you can tolerate the cigar smoke even if you have a low ceiling. And just our luck, we don't have a very good fan blowing during most of the year here in Los Angeles. We have very light winds. The average wind throughout the summer months is about 5 miles an hour, and it consists of winds blowing maybe 10 to 15 miles an hour with the sea breeze in the middle of the day, and winds blowing maybe 1 or 2 miles an hour during the night. And the next slide is just to show what happens to the air when you have that situation. Oh, I'm sorry, I forgot one. Will you hold this and show the next one and come back to this? As long as I introduce this motion a bit, I'll pursue it. Here you have the path, computed path of air moving across the Los Angeles basin. This is way back when I was with the Air Pollution Foundation in 1954. The situation meteorologically hasn't changed since then. What has changed is the figures below it showing how much traffic and so forth there is. Let's not pay attention to that. But as you see, what this is a map of the Los Angeles area. Here's the coast, here's Santa Monica at the upper right of the coastline, and then you go down past Redondo Beach, the Palos Verde area, Long Beach, and on down the coast. And here's downtown Los Angeles, the center of all these circular closed curves, San Fernando Valley and San Gabriel Valley and on inland. Well, what I've done here is said, supposing that we try to follow a piece of air, actually in this case a piece of air aiming to arrive at Burbank at a particular time. But the main point is to see what happens to this air, this one that's labeled number 1 out here over the coast in a little square. You see, with the sea breeze, it starts, I guess, at about 4 in the afternoon. 1600 means 4 in the afternoon, if that's what it says. And every hour, there's a point where it has moved. Oh, I guess that's 1500, 1600. It moves quite a distance from offshore onto the coast, and then with the sea breeze continues moving fairly rapidly inland, then more slowly inland, and then it turns around with the land breeze, and you see it moves just a short distance, 2 or 3 miles at a time, all the way through till the morning at 6, 7, 8 o'clock, and then it starts up with the sea breeze again, first slowly and then more rapidly. So you can visualize what's happening to this air. First, it's moving fairly rapidly across the coast, and even though the traffic may be fairly heavy and it passes near refineries and so forth, it doesn't get very high concentrations. But then it moves more slowly in the evening and moves across various sources of pollution and picks up pollution, and then it moves slowly backward through the night, continuing to pick up whatever pollution there is. And in the early morning hours, the early morning rush hours in this particular case, it's moving over an area of very heavy traffic, very slowly, so it picks up a lot of pollution, and in this case then it moves on from there and reaches Burbank, in this case with a high oxygen concentration, that's mostly ozone, and a high eye irritation effect. This other one starts and even though it starts fairly close, having started I guess a little later, it follows a different trajectory and moves around. But you see that it does the same thing. It moves in a certain distance, and then it moves out, and now you can sort of visualize that the next day it would be carried back, and then might do the same thing again. Eventually it'll get out, but it may circle over 2 or 3 days, going first in with the sea breeze, then back out, and then in, and then out, and then finally out through one of the passes or up over the mountains. Well, let's return to that previous slide. This is just to emphasize the fact that inversions aren't the sole property of Los Angeles so far as the nation is concerned. These are what are called surface inversions, and this is an annual basis, percentage of total hours estimated to be, and you see that in some of these areas, like the Great Basin area, and an area over here just east of the Appalachians, you have as much as 45% of the hours there's an inversion right down at the ground. Now these may be just the nighttime hours and many of the daytime hours not having inversion, but there are periods when the inversion occurs both day and night over these areas for several days at a time. And one such example, some of you may remember the Dornora incident, when they had a day and night inversion for about a week in this little valley near Pittsburgh, and 20 people died as a consequence of the pollution, in that case from steel mills which were operating while the inversion and light winds persisted. So you see that there's practically no place in the United States where there isn't the potential for high pollution concentrations if you have these sources. And as the metropolitan areas spread and higher industrial and domestic concentrations of activities develop, more and more places will be affected by high concentrations of pollution. Well, we turn now to the question of what are we doing about it, and what success have we had? There's nowhere in the world where there's been more done about pollution than in the let's have the lights for a minute, please. There's nowhere in the world that has done more in the attempt to control pollution than here in Los Angeles County. The work here has been exemplary and has actually shown the way, insofar as the way has been shown, for the entire world. Already in 1945, there was concern with the problem, and the city health department had a man here, brought here actually from Chicago, to attempt to cope with the problem. By 1947, it was recognized that this was a problem which couldn't be handled by a city by itself, that municipalities polluted each other, and so it needed something larger, and the state passed the law which enabled the establishment of the county air pollution control district. 1947 then and 1948 saw the beginning of control measures, and the first control measures were aimed at the control of sulfur dioxide, and then control of particulate matter, dusts and fumes from various industrial activities. And little by little it became clear that the refineries were making large contributions, and they were required to control their effluents, and the recognition that the backyard incinerator, which was the pride and joy of every householder in the Los Angeles area, one got the impression when the attempt was made to outlaw burning refuse, that there was nothing dearer at all to the heart of the American householder than his backyard incinerator, even dearer than his television set. But at any rate, in spite of all the resistance, the backyard incinerators were outlawed, and even the burning of refuse in municipal incinerators, which were found to be inadequate. It was impossible to avoid a considerable amount of pollution from them, and so they were outlawed, and we have this process of collection of the refuse and using them for landfill, which will create problems of a different sort eventually when we run out of land to dump them. But at any rate, all these things were done, and finally it was recognized, and when I say finally, actually, I might mention that already back around 1948, as a result of a study made by my colleague Professor Ettinger, I collaborated a little bit in, we came to the conclusion that much of the pollution must be coming from automobiles even that early. But the real definitive demonstration of it came in 1950 and 1951 when Professor Hagenschmidt of Caltech demonstrated that most of the phenomena which we characterize as smog, the eye irritation, the high ozone content, which would in those days cause rubber cracking. Now the tire companies have made improved rubber that doesn't react the same way. But at any rate, all these various phenomena, eye irritation, damage to vegetation, and so forth, were reproducible from, first of all, hydrocarbons such as came from refineries before they were controlled, but second of all, the automobile exhaust that we saw yield about 10% unburned fuel plus oxides of nitrogen, which together cause this photochemical reaction. So the County of Los Angeles has been working very hard in the attempt to control pollution, and well, let's see first of all where we stand and where we've been and where we're going. So the next slide shows it's a table, unfortunately perhaps a little hard for a person to gather. Let's look first of all at this total amount of pollution down in the lower right hand corner. The total amount of pollution per day entering the atmosphere in Los Angeles is estimated to be 14,600 tons. 14,600 tons per day entering the atmosphere. Of this, you see, most of it comes from the gasoline-powered motor vehicles. And actually, if you look in the next column to the total, you see that most of that is in the form of carbon dioxide. But a very large amount of it over here under total organic gases, which means the hydrocarbons mostly, 1,870 tons per day from motor vehicles compared to a total of all organic gases, 2,700 tons. Two-thirds of the pollution in the form of hydrocarbons, for instance, is coming from automobiles. This NOx is oxides of nitrogen. Nitric oxide is NO. You can replace that X with a 1. Nitrogen dioxide, NO2. Replace that with a little 2. And you see that gasoline-powered automobiles produce a total of 540 tons per day. Now the combustion of fuels produce about 3/5 as much, 300 plus tons per day, but the gasoline-powered motor vehicles more than half of the total amount of oxides of nitrogen. On the other hand, when it comes to sulfur dioxide, which is another serious, well, one of the main troublemakers in areas where they burn coal and petroleum in large quantities. The burning for power and for, well, we don't use oils for home heating, so it's burning for power produces practically all of the sulfur dioxide. Now, during this Rule 62.1 period, this Rule 62 and 62.1 govern the times when the power plants can use petroleum oil and when they have to use natural gas. 62.1 period means the period when they're permitted to use oil. That's the periods from November through April, but starting in April 15th and going into November 15th, they're required to use natural gas, and then this number would not be present, and this would be a much smaller total. But just keep in mind then this total of almost 15,000 tons per day. The next slide shows us a little easier numbers to gather, the numbers in terms of percentages. 69% of the hydrocarbons and other organic gases come from gasoline-powered automobiles. 98% of the carbon monoxide, 59% of the oxides of nitrogen, 1/3 of the particles which reduce the visibility in the air. And so you see that the automobile actually is, and this is after the crankcase devices have been in effect. You see, this is January 1967. The automobile is the principal contributor to our pollution. The combustion of fuels, particularly during this winter season, is responsible for another large contribution, and almost the only contribution of oxides, sulfur dioxide. Well, what effect does putting all of this into the air have? Well, I didn't want to go into much detail about that. I'll just show you one slide, the next one, which gives the highest concentrations experienced in, well, I shouldn't say in the Los Angeles basin, but at the regular monitoring stations in the Los Angeles basin. 72 parts per million concentration of carbon dioxide is the highest that was ever experienced right in downtown Los Angeles at various times, in 57, 59, 1960, at Burbank as late as 1963. Might mention that in contrast to this 72 parts per million, the carbon monoxide content when you smoke is something like 40,000 parts per million. So you can be greatly encouraged by the fact that smoggy air isn't quite as bad as what you inhale if you smoke cigarettes. Well, the concentrations of hydrocarbons, depending on how they are measured, these are two different ways of measuring, I won't go into that, but about 5 parts per million or 40 parts per million. 40 parts per million is quite high, 5 parts per million is plenty high too. The usual concentration on an average smoggy day is 1 part per million. Oxides of nitrogen. Well, if we had this concentration for any length of time, nowadays it would lead to a smog alert. 3 parts is considered the level of an alert, but we've had alerts only due to the ozone content. When the ozone goes above 1/2 part per million, we have an alert stage declared, first stage alert. When it goes above 1 part per million, we have a second stage alert, 1.5 parts per million, a third stage. And you see, we've never reached the second stage alert. The first stage alert, people are politely requested to stop doing what they're doing. The second stage alert, the sheriff's supposed to be able to stop automobiles and stop industrial activities and so forth, but it's never been reached, so we don't know whether they'd ever succeed in stopping things. Sulfur dioxide, similarly. Now the average, this is a very high value, and it is thought that this value was attained when air directly from the plume of some chemical plant went right down to the station, because the usual thing, and almost never do we get more than a part per million, and the usual thing is 1 or 2/10 of a part per million, even on a bad smoggy day. So this was very unusual, and it was before this rule 62 was put into effect. We never get concentrations like that anymore. So these give you some ideas of some of the concentrations, and when the ozone is anywhere above about 0.2 parts per million, usually we have eye irritation. When it gets above 0.4, then you have very severe eye irritation and headaches and nausea and a lot of other symptoms. The next slide gives you an idea of how frequently these... Now, back in 1960, the state established standards of tolerable air. And you see that excepting for the sulfur dioxide level, which, as I've indicated, has been reduced by Rule 62 and never was really very high in the Los Angeles area. Well, in the case of ozone, year by year you always have about 200 days in which the acceptable standards of clean air are exceeded according to the levels established by the state. In the case of oxides of nitrogen, about 100 days. In the case of carbon monoxide, about 30 days on the average, quite variable. 1965 appears to have been the worst year so far as carbon dioxide was concerned. And then so far as particulate matter in the air, you see you have about 150 to 180 days. So more than half the year here we have unpleasant, intolerable air. And if you notice, there really isn't much of a trend. Some years were small in one pollutant and somewhat more frequent in another. But here, for instance, as recently as 1965, we had 58 days with carbon monoxide exceeding it. As recently as last year, we had 214 days with ozone values exceeding the state standards, and so on. So it doesn't sound as though we're doing very well. Well, let's look at the trend to get some idea of what's happening and what we can expect. The next slide, please. The trend of hydrocarbons and other gases. This starts in 1940, and already at that time the petroleum industry was engaged in certain activities, not for the sake of cleaning up the air, but because they could do a more economical operation. And in that process, they were reducing the amount of hydrocarbons estimated to be leaving their plants. And you see, they started with more than 2,000 tons per day, and by 1950 they were down to 1,000 tons per day. But then, starting then, they were required to engage in a very active control program, and that brought it down to less than 200 tons per day. About 150 tons per day is where they have leveled off. So throughout this period, the petroleum industry has been reducing its contribution. What about motor vehicles? Well, the motor vehicles has been continually increasing. These are estimates based on the number of gallons of gasoline consumed in the basin, and increased until the control program with the crankcase devices, and then it's estimated that that caused a leveling off and actually even a little bit of a reduction, primarily still due to the crankcase device, but contributed to, according to this estimate, by the exhaust controls that started being put on the 1966 cars. So this gives a net result that during this period we had first a reduction and then an increase, and now we're getting a little bit of a reduction. Now this projection here is based on the continuation of an effective automobile control program which will maintain a maximum allowable concentration of 275 parts per million in the automobile exhaust up to 1970, and then in 1970 it's supposed to have a still more stringent control. But with the present projection, you see, we will be just a little better off than the best we've been in the last 25 to 30 years. The next slide shows the same sort of thing for carbon monoxide. In carbon monoxide, the main contributor has been the motor vehicle. It's continually increased. There's been some control of carbon monoxide in metal industries and refineries, so there's a little bit of a leveling off and then an increase, and now a decrease due to the exhaust devices, presumably. So we're at an all-time high of about 10,500 tons per day, and maybe we've had a little bit of increase. The projection is that with the exhaust control devices there will be a further decrease. The next one shows the oxides of nitrogen. In the oxides of nitrogen, you see that so far there's been no attempt to control the oxides of nitrogen as such. Using natural gas has caused some estimated decrease. It showed how natural gas seems to produce a little bit less. And so there's been a little bit of a leveling off here. But you see the amount of oxides of nitrogen has been increasing. It's well above 900 tons per day now, and the projection is that it will continue increasing, and I don't know where it'll stop. And one of the reasons why it hasn't been controlled so far is that nobody knows how to do it. There's some work been done here at UCLA which seems to suggest that there are potential ways, but the success has been minor, and it hasn't been very practical from the standpoint of the mass production of vehicles. So at present, oxides of nitrogen are completely uncontrolled, and there's no prospect of their being controlled. There's a serious question as to whether, when you control hydrocarbons partially and allow the oxides of nitrogen to continue to increase, you're not worse off so far as eye irritation and other aspects than if you did not if you did not reduce the hydrocarbons. Well, I won't go into that, but because I certainly don't want to encourage anybody, or let's say to discourage anybody from trying to control the hydrocarbons. But this illustrates the fact that even if one is able to control the hydrocarbons and carbon monoxide, we still, as a result of the internal combustion engine being the device which gets us around from place to place in the city, we still will have a large amount of pollution of a type which can be ultimately quite serious, to have serious effects on health. And for this reason, well, I can just add that it's my personal conviction, based on a lack of expertise in the subject of civil engineering. It's my personal conviction that the hydrocarbon and carbon monoxide controls will not be nearly as effective as is hoped or claimed. But be that as it may, certainly we see the evidence that internal combustion engines will continue to spew forth other forms of pollution, and it's my hope that we will move to other forms of locomotion in the form that suggests itself as the electric automobile. Well, be that as it may, in Los Angeles now we have had rather effective control. May I have the lights for just a minute, and then we'll zip through the last 3 or 4 slides in a hurry. Los Angeles, we've been making serious attempts at control. And with these serious attempts at control, we have sort of leveled off. It would appear that at least things aren't as bad as they would have been if the controls were not put into effect. In the East, for instance, or practically everywhere else, industry has not been controlled. The burning of trash has not been controlled, and so they're far behind where we are, and the prospects are not very promising that they'll be very successful in catching up. So that these skyrocketing curves can be expected to be extrapolated for longer periods than here in Los Angeles. Now I want to talk a little bit about the worldwide prospects, and to do that I want to illustrate first of all what happens when you have effluent, some kind of source of contamination coming from a single smokestack. And the next slide illustrates that. The idea is that this smokestack is at an elevated stack, the usual thing, and so the highest concentration at the ground is not right at the position of the stack, of the source, but a little distance downwind. And I've also assumed that there is some background concentration, some pollution that's in the air from somewhere way back. And what happens then is that as you go downwind of this stack, you have an increase to the position where the pollution is carried downward from the source to the ground, and then gradually spreading due to the turbulent wind. It gets more dilute. So the concentration of pollution, which is shown in the vertical, and this is downwind in kilometers. A kilometer is about 5/8 of a mile. So that downwind you get a gradual decrease, and it comes down in a few kilometers almost to the original background. And now ordinarily you don't have a single source, but you have a whole series of sources, especially in a metropolitan area. And the next slide illustrates that, where now we have a reduced scale in the vertical, and you have, say, this might be the curve that we saw before, but after you go a little distance downwind, then you may have another contribution of another stack. It may be off to the side, or it may be not as strong, but it'll add on, and each one of these bumps is supposed to be the effect of some other stack adding on. And you see that what happens then, instead of coming down to a constant background the way the other one did, you have a gradual building up. And as long as you pass new sources, you have a continuation of a building up of the general background level. Now, well, mathematically it's hard to deal with a lot of discrete sources of this sort, and so we deal with it as though you have them all evened out over an area. And the next slide shows what happens when you have an area source. You assume that the sources of pollution extend over this dark distance here along the downwind distance. And as long as you have that dark area adding pollution, the amount of pollution, the general level of pollution climbs up, reaches the highest at the end of the source region. And then the spreading out and diffusion sort of visualize it, supposing that this is Los Angeles, and you have the air getting all polluted, and then it spreads out after you've crossed over the San Gabriel Valley and on eastward. Maybe by the time you reach the desert, it spreads out and gets real thin, but then it'll pass over another city and then another city, and the next slide illustrates that. Here is air coming in from the Pacific Ocean, relatively clean, and here's the effect over Los Angeles. Now it falls down, maybe Las Vegas contributes a little bit and so forth. Comes down and across the Rocky Mountains, it passes Denver, it gets a little bump, it goes down, and then it passes, I've forgotten what this is supposed to be, but there's Kansas City, and there's St. Louis, and there's Chicago. And when you get east of Chicago, then you don't get any chance to have it go down very far before it passes another city, and another city, and another city. And finally it comes over the Atlantic Ocean, and then it gets a chance to go down. And hopefully, by the time it gets around the Earth and comes back to Los Angeles, it's down where it started. Now, how would it get down where it started? Obviously, the atmosphere must not just be spreading it out, but also cleansing itself. And to some extent, we know that the processes by which it cleanses itself, and pollution is removed by various processes, so that the atmosphere may be nearly cleansing itself. Now, we know that there are some things which come about from the burning of fuels which do not go all the way back to the original level, because we know that in the case of carbon dioxide, which is not an objectionable pollutant in the sense of being poisonous in the concentrations that occur, carbon dioxide has increased in concentration by about 10% in the last 50 years. And so we know that it's been gradually building up. We don't know enough about these other pollutants, which are more toxic, whether they've been building up or not. But if they haven't so far, we can visualize that gradually we'll start putting in the pollution at such a rate that it will be. And then we'll have a situation such as the next slide shows. And you see that this is just that first time, this bottom one, that first time. And maybe after going around the Earth, it'll start just a little bit higher. And maybe this is the 100th time around the Earth. And this is the 200th time around the Earth, and the 300th time around the Earth, and the 400th time. But you see, or maybe it's thousands of times around the Earth. But if it's going to be building up this way, eventually, actually, the concentration that we start with is higher than the objectionable concentrations that we have right now. You can sort of visualize the pollution building up not only locally, but also the background level building up as a result of the continual putting in at a rate faster than it can be removed. And that is the basis for my concern that perhaps within a century, unless we take a more fundamental and more drastic action in controlling pollution, we may reach the stage where everywhere on Earth the concentration of pollutants is so high that it cannot support life, that it'll poison all humanity and all sensitive animals and plants and leave a deserted world for a few centuries, perhaps until life starts again with the amoeba. Well, this is not a very pleasant prospect. I should emphasize, of course, that this is entirely schematic. You'll notice it says schematic on each of these slides. The air which reaches the air which leaves Los Angeles doesn't go direct to Denver and then to Kansas City and so forth, but some of it goes farther south and some of it goes farther north. It weaves around and mixes, so forth. So at present, you don't have the same kind of building up as is shown here. Usually the pollution is mostly local, although in the east you do have pollution from one metropolis reaching the other already here. But because the metropolises are close enough together. But at any rate, this general idea certainly follows, and especially the idea that if we add pollution at a rate faster than is going into the atmosphere, if we add pollution and have it go into the atmosphere faster than it's being removed, you'll gradually build up the concentration everywhere, so that not only locally will you have the smog incidents of Los Angeles, Denora, London, etc., with increased health hazards and deaths, but also on a worldwide basis. The lights, please. May I have the lights, please? In conclusion, then, I just want to say that it's gratifying to know that there has been an increased concern. A few years ago, Los Angeles was going it alone. Los Angeles was attempting to influence the automobile industry to take action to develop methods of controlling the hydrocarbons and carbon monoxide, etc., from the exhaust, and getting nowhere. Gradually, as the entire state became concerned, and now as the entire nation has become concerned, there has been more response on the part of the auto industry, and there's been more response on the part of various agencies and various industries. On a worldwide basis, too, there has been increased attention, and there's been an increased awareness. Not that anywhere else has there been nearly the degree of willingness to pay the costs in terms of costs to industry and costs to the citizens. But at least there is this awakening, and we can hope that before we reach this situation where the world everywhere becomes unable to support life, we will have established the controls, and life will not dwindle from the earth. Thank you.